Okay, we have spent so much time calculating and thinking about uh, what happens if you have a net force, what happens when you are accelerating motion and changing and predicting it. We probably didn't stop to think what happens when things are not moving, not changing. So we'll take a little break from serious physics and do statics. And it's actually, look at your homework, it's surprisingly complicated at times. What if things are hanging or sitting at a weird angle? I have this cool bird that I probably can't balance on my finger, right? And if you hold it, it feels kind of weird. I guess I could sanitize and let you hold it, but it's a fun toy because it will balance like right on its beak. How is it doing that? Why shouldn't it? Well, the wings are balanced side to side, but why shouldn't he like fall back towards his tail? The tail hangs way out there. Shouldn't he tip over? Actually, no, definitely not, because he doesn't. Okay, well, we'll do our first example of like a hanging sign. Okay, so this weird trapezoid is like a sign or a weight, and the two cables are holding it. They make 60-degree angles with the ceiling. So this is what this chapter for me is really fun with geometry, and the geometry is fun even years and years after the physics has become boring and stale. But I still enjoy this geometry. So we have 60-degree angles there. You'll always get some random angle, and the object just hangs there. But we know that it weighs 5 newtons, and if we've got two equal 60-degree angles, we can actually figure out what the tension is in each cable. Okay, you'll often see some kind of mysterious, oh, there's the bell. Some mysterious challenge physics questions like, oh, things are hanging, and you've got some angles, and but you're still supposed to know physics and be able to figure it out. Okay, well here I'm giving away the tricks today. Well, even if I can't figure out my technology. So it's in equilibrium. That means the sum of all the forces in the x direction. So we approximate this thing as a dot, a free body diagram, like in chapter 4. Sum of all forces in the x direction has to be 0, and the sum of all forces in the y direction has to be 0. That's what's printed on the notes. And what the book will sometimes use this Greek letter sigma, that weird sideways looking staple letter. In fact, to learn it, I just started writing it in place of the capital S. That's what it means. Okay, same thing. It stands for sum. Well, okay. So what we actually have here, tension, if you remember, tension along a rope is at every point on the rope. So we have free body diagrams here. And if you forgot your geometry, you need a refresher. If the angle between the cable and the ceiling is 60 degrees, what other angles will be 60 and what will be 30? And they'll be at 90. 90 degrees is just between straight down and the ceiling. Okay. Hopefully you realize these guys here at the bottom are also 60. Okay, so in the x direction, all we have is plus the tension in the right rope times cosine of 60 degrees minus the tension in the left rope, cosine of 60 degrees, equals 0. And that's pretty helpful because you could solve that and get the tension in the right equals the tension in the left. We'll use that fact later. So since they're symmetrical angles, you can just solve for each other. If they weren't symmetrical, you'd have a slightly more challenging problem, but look, the difference is just the ratio of the cosines. So you could solve for either tension right or tension left, just in terms of the other. In the y direction, we get a little more help. Sorry. Okay, we'll do right to the ceiling there. So in the y direction, we'll have the sine components of these vectors. And what's really nice is if you're completely lost, it's a statics problem. Everything has to add up to 0. Nothing accelerates. There's no net force. It's just sitting still. Okay, so if I correctly do everything, both of these would point up, so plus TR sine of 60 plus TL sine 60 minus mg equals 0. Okay, does anybody still need those? I can start scrolling up. So it really just takes some intuitive understanding of vector forces, and okay, everything has to cancel out. Nothing can be net force because we have no acceleration. It's static. Wait till the next problem and see how complicated they become. But okay, I can replace TR with TL. So let's see, it lists TL first, so why not? I can simplify, I can replace TR with TL, 2 times left tension times sine of 60 equals mg. Because if I subtracted mg equals 0, so I just manipulated the y equation. Sine of 60, I know what that is. So TL times 2 times root 3 over 2, right? And mg was 5 newtons. Probably 0.5 kilos. Okay? So we just do some math and solve it. I actually like. Technically, that's not allowed in math. What was that, 2.89 newtons? Yeah. And that has to be the right one as well. Why are you not allowed to divide by radical 3 in math class? But you're right. So in math class, you're not allowed to divide by irrational numbers. Why not? Yeah, they would make you simplify it. On my test, though, I'm always going to simplify into like 3 sig figs and round. So you have to do the calculator. I don't mind you writing that or simplified that. But your calculator can do it anyway. So why not? It is forbidden. But why is it forbidden? Do you know your calculator is just doing the hand-by-hand arithmetic that they taught you in elementary school? It's just moving the digits around to subtract and calculate. How many digits does square root of 3 have? It has infinitely many. And so your calculator, when you do this in the calculator really isn't doing that. It's truncating, it's rounding off at 8 or 9 or 10 sig figs or something. And so a mathematician just disgusted with themselves. They aren't allowed to divide by a radical, by an irrational number, because you can't actually compute that. It's the same reason you can't divide by 0. But this is physics. We know about sig figs. You can totally divide by that number. I only care what it is to 3 sig figs anyway. So give it 4 digits or 5 if you want to be really particular. It's fine. Numbers are just numbers. We can only measure so close. Okay. Any questions about that one? Ooh, give it a thought while I cut the video, because we're at almost 10 minutes. What if we have something balanced? Oh, and I was going to get fancy and like hang 2 things from this somewhat balanced meter stick. Got a meter stick on my table, and it's actually off balance. In fact, I want to make it, so I put it at 50 there. I want to make it like more off balance. It tips to one side. Okay, but let's see if I can get it. If I balance it somewhat carefully, it will tip but not fall. Why is it hanging lower on one side than the other? Like that. Very nice. Okay, did I pause this? Nope.